Hey guys, we've got 1.5 liters of buffer. It contains 0.25 moles per liter of the acid, hydrofluoric acid, HF, and 0.25 moles per liter of the conjugate base, in this case, sodium fluoride. We want to know what the pH is after we add an extra 0.05 moles of NaOH. NaOH being the base here. Now, let's take a look at what we've got. We've got our HF, and it's in equilibrium with H plus and F minus. Now, some people may say plus H2O here and convert this to H3O plus. It's the same thing. Don't worry about it. What I want to know is how many moles of each of these do I have? Because in the end, I need to move 0.05 moles of acid towards the base because I'm neutralizing the acid away. Here's what I mean. We're going to calculate the number of moles for each of these. The number of moles for HF, concentration times volume, 0.25 moles per liter times 1.5 liters. Turns out to be 0.375 moles. I think you'll find that we have 0.375 moles of this as well before we add our NaOH. But then we add 0.05 moles of NaOH. And what does NaOH do? It titrates away acid. We're going to lose 0.05 moles of acid, leaving us with 0.325 moles of it. And where does that acid go? Well, the H reacts with the OH here to make H2O. That's called neutralization. And this F becomes the conjugate base because you added base. Get it? Anyways, if you lost 0.05 moles of acid, you gain 0.05 moles of the conjugate base, and you end up with 0.425 moles of it. That's all well and good, but how's that going to help us find the pH? Well, you have two options. The first is to do an ice table with your Ka that's given for hydrofluoric acid and this stuff here. But because it's a buffer, there's also a shortcut. And that shortcut is the Henderson-Hasselbalch equation, where if you're given the Ka or pKa of the acid, and then the amounts of acid and conjugate base, these can be concentrations or technically numbers of moles. Don't tell anyone I told you that, but you can plug moles in here. You can actually just solve directly for the pH. So here we go. What's the pKa? Well, to find pKa, you take the negative log of the Ka, which was given to us. That's a number, we got it. Plus the log of base over acid. Usually concentration, but shh, you can also use moles. Base is 0.425, 0.425. Acid is 0.325, I'm told. Yeah, exactly. And so we have a formula that we can just plug into our calculators. Let's do this. What we have is the Ka, 3.5 times 10 to the power of negative 4, but the negative log of that, which gives me 3.46, plus, and then the log of this ratio here, 0.425 divided by 0.325, and the log of that, which is 0.117. Add these two together. I get 3.58, and that's the pH of this solution once you add some NaOH. Now, notice, just for old time's sake, if, before I had added the NaOH, the concentrations of base and acid were the same. So this cancels to 1, the log of 1 is 0. When you have the same amount of acid and conjugate base, pH equals pKa. So before we added the sodium hydroxide, The pH here was the negative log of this. It was that 3.46. Then we added NaOH base, and the pH went up. That's good. Story checks out. I'm confident in this answer. Best of luck to you and your buffer questions.